Today we're going to do section 8.2 on page 820. But before that, I want to again remind you of the distance formula. This is this is the same thing I reminded you in the previous video, because we're going to be doing almost the same thing here as we did before. Okay, so make sure that you understand this formula. This is on page 91, and understand how example 5 on that page is done. So that, and then the other thing that I also want to remind you that I already did last time is how to solve equations with radicals. This is on page, I can't, it'll zoom in a second. What is that, 155? Yeah, anyway, on for example 7, which we solve a radical equation containing two radicals. Very important that you know how to do this. Yeah, this is in your book, page 155. If you have any problems or any questions about it, please review that part. That's in chapter 2.6. Now, once that's done, then you will be ready to do what we're doing today, which is deriving the formula of the hyperbola, which goes almost identically to the deriving of the formula of the parabola. What did we do last time? Ellipse, yes. So it's almost identical to the ellipse, except that with just one small difference, okay? And so please turn to page 820, and let's look at what a hyperbola is. Now on 820, it shows a picture of a hyperbola in the middle of the page. A hyperbola, it consists of two parts. The one part on one side and the other part on the other side, and they're symmetrical. And they just go in and then go back out, and they go infinitely. So in that sense, hyperbola is quite different from the ellipse. In the ellipse is a closed, is a bounded object, right? It doesn't go on somewhere forever, whereas the hyperbola goes on forever. And in both, it consists of two halves. Okay, each half is symmetrical to the other one, and then they both take off to infinity. Is similar to the ellipse in that the hyperbola also start with an a. Okay, there's an a here, and then there is an negative a on the other side, and it also has two focal points, just like the ellipse. We have a c, 0 on this side, and then a negative c, 0 on the other side. And then you will also draw a distance from the focal point to any point on the hyperbola, such as x, y. The difference, however, is that there is no string that you're going to draw anything out of. The hyperbola is defined as the difference of the distance being constant. Now, the ellipse, from the last section, we said that the d1 plus d2 equals to a constant, which was 2a. In this case, it's a d1 minus d2 equals to 2a. That's the definition of the hyperbola. And so hyperbola, in a way, is almost like an ellipse getting turned inside out. But let's not think too much about that, because that might sound repulsive. Anyway, so that with that definition alone, okay, we are going to derive the formula for the hyperbola. That is, the hyperbola is defined as all the points such that this distance to one focus and subtracted by the distance of the other focus is constant. That is, d2 minus d1 has to equal to some constant. And then we're going to figure out what the constant is. So I have a hyperbola drawn here. It's much poorer than the picture in the book, but it will help me explain this a little better. The hyperbola, we're going to figure out what is d1 minus d2. What happens is that, so the hyperbola is defined as d1 minus d2 equals to some constant. And what might the constant be? What happens is, if you draw the point and consider the point down here at this point, okay, that is at a comma 0, then d1 goes, the d1 calculates from one focal point, and this one is, I should write it down, negative c comma 0. And then the one over here is c comma 0. So from here to here is is D1, and from here to here is D2. But D2 is also this part. So if we need D1 minus D2, that's this whole thing minus this part. So in other words, D1 minus D2 is this part. This part is exactly 2a, because half of it is a and the other half is also a. So together, D1 minus D2 equals to 2a. And that's how we're going to derive the equation of the hyperbola. Now that we know that D1 minus D2 is a constant, and the constant equals to 2a, that's the definition of a hyperbola, now we can come up with the equation for it. So please look at page 821, where I'm going to go through this. This is identical to what we did for the ellipse, nearly identical with a very slight difference, okay? But we're going to go through it again because I feel that this is very good practice for you to learn how to manipulate a whole bunch of symbols and not be and feel comfortable about it. So let's do that. So what is the first lesson? I have D1 minus D2, well, whatever, okay? The point is, one of the distance, the longer one will subtract by the shorter one. So this, yeah. Anyway, so we'll take this one, we'll subtract by this one, and that will be the distance of these 2 points subtracting we'll write it as x minus negative c, okay, which is the same as x plus c and squared, plus y minus 0 squared, following the distance formula, and then take the square root, and then minus, okay, that's the long side, minus the short side would be, the distance is, well, anyway, well, yeah, we'll worry about long and short later. Right now, let's continue doing this. So the other part is at that positive c, so we'll have x minus c, and then plus again y minus 0 is just y squared, okay, squared, everything's squared, and this is supposed to equal to 2a. All right, this is an a there. All right, so far so good. So the next trick we are going to do, as before, is we're going to move this thing to the other side of the equation, and then we're going to square both sides. All right, so I will write that down. So I have moved this piece onto the other side of the equation. Okay, here's the equal sign. So now we have 2a plus this stuff here. And then this one, I changed the minus into a plus. So far so good. And the next step we're going to do is square both sides. Now to square both sides, this one, it will get rid of the square root. So we will just have the x plus c squared plus y squared left. So that's good. Now this side, we'll have this thing squared, and then this thing squared, and then this times 2. Okay, following that equation that it was up here, and I erased it, so I'll draw it here again. So u plus v squared equals to u squared plus 2uv plus v squared. If it was a minus, then this sign turns into a minus. But right now we're dealing with plus, so we'll follow this formula to multiply this stuff out. So that will be equal to 4a squared plus that times 2, that will be 4a square root of this thing, x minus c squared plus y squared, and then this thing squared, which is plus x minus c squared plus y squared. All right, so that is so far so good. And I think at this point we can get rid of the y squared because it appears on both sides, so they cancel themselves out. And then we need to multiply this thing out. This part, okay, is following this formula right here. Okay, this part equals to x squared plus 2xc plus c squared. And similarly, just this part equals to x squared minus 2xc plus c squared. Now, and I haven't done anything to these. Now, you notice there's an x squared, okay, and a c squared here, similarly on this side. So those also can be canceled out. because they appear on both sides of the equation. So these, however, cannot be canceled out. So we'll move these things to that side of the equation. So we'll have 4xc left on this side of the equation. So we'll have 4xc, okay, and then equal to, copy down, okay, and then so that equals to 4a squared plus 4a times the square root, all this stuff, x minus c, all this has to be written down, y squared, and then yeah, and then we took care of these. All right, and then I also want to move the 4a squared to the other side of the equation. So let's move this. So 4a squared, let's move it over here. That becomes negative 4a squared. 4a squared. Is that right? Let me check. Okay, see if I made a mistake. It's correct, okay, unfortunately, because I was hoping we can go a little faster, but there is no going faster. There should be a plus sign there because I'm moving 4a squared to that side, and this thing was positive. So, well, there isn't a whole lot we can do except we can at least cancel out the 4. We can factor out the 4 here and the 4 here, and they cancel themselves out. So that is pretty good. And after that, there isn't much canceling left to do. And the only thing we can do now is square both sides. So this side then becomes, this side, okay, then being squared, it will become something like this. Let's see. We have minus a squared. Again, we apply this formula, okay? That will become a to the power 4th. That's minus a squared, and then minus, let's see, xc, and then a squared. That's this thing times that thing, ignoring the 4s, but not ignoring the negative sign. The negative sign is still there. It didn't get canceled out. Plus, isn't there 2 of them? That times that? Yeah, I think so. Because it says right here, u plus v squared, there's a 2. Okay, and then the x squared c squared should be on there, okay, and then on the other side there's an a left, so a will become squared, being that we're squaring both sides, and the square root will simply disappear under being squared. So x minus c squared plus y squared, something like that. Okay, let me send on this side and double check. Now everything looks okay. So the next thing we're gonna do is let's multiply this stuff out, okay, leaving these things for now. So then we'll have this equal to, this thing multiplies out to be a squared times, with a minus sign, only this part will follow this formula, except this part turns into a negative, okay? And so we have x squared, and then minus 2xc, and then plus c squared, and then plus y squared. And that will be equal to a squared, and then x squared minus 2x. What am I doing? I just keep copying. I'm falling into a trance. So let's multiply the a out with all the rest of the stuff. Let's get rid of that. Okay, so that becomes a squared x squared minus 2 a squared xc plus a squared c squared, and then finally plus a squared y squared. Okay, and then let's see if there's anything we can cancel out. Right here, this thing is identical to that object, both negative signs, so this can be canceled out. Okay, I think that's about it. Everything else stays. And so now we're going to keep everything that has x or y in it on one side of the equation. So let's keep this thing here. Okay, x squared c squared will be on this side of the equation, and the a to the power 4th, we'll put it on the other side because it doesn't have any x's in it, and it has a negative sign, being that it got moved over. And then plus, so this one is, where'd this one come from? oh, never mind, it's fine. So minus a squared x squared, being that we moved it over here across the equation sign, and then that one stays, so will be plus a squared c squared, and then this one move over, it will become minus a squared y squared. Okay, that is so far so good. The next thing we're going to do, I think we're going to do the same thing. We'll set b squared equal to c squared minus a squared. Okay, that is, we're going to let b squared, I don't think I'll write it here. This is just like before. We'll let something called b squared, let b squared, set b squared equals to a squared minus c squared. Is that what it said? Wait a second. Or is it c squared minus a squared? I think I got it backwards. Yeah. Let's well, whatever. This is similar to before, but the sign might be flipped around. So we will have. I'll write it. Let's see. Where do we write this? Write it right here. B squared. We'll set b squared equals to. Let's see. What was it? I keep forgetting. C squared minus a squared. Okay, c squared minus a squared. Okay, and this is what we're going to do here. And so that what happens if b squared equals to c squared minus a squared, then this thing factors into this becomes x squared b squared. Okay, being that b squared is c squared minus a squared, and then minus a squared y squared. And this side, if we factor out the a squared, then we get c squared times c squared minus a squared as well, which, like we said, we want to call that b squared. So then we are getting, this looks very similar to what we did in proving the ellipse equation. So the next step we're going to do is divide. So this part is just equal to a squared b squared. And we're going to divide everything by a squared b squared. And once we do that, so let's divide a squared b squared across the board. Okay, a squared b squared. And so is this. And once we do that, then that part then equals to 1. That's what we're driving for. And this part, the b squared cancel out, and we have x squared divided by a squared minus, and then y squared divided by b squared, and that equals to 1. And that is the equation of the hyperbola. Now the equation of the ellipse is the same thing except with a plus sign. That's the only difference. So this whole step we went through here, this is identical to what we did for the ellipse, except for this minus sign right here, which landed right here eventually. Otherwise, the operation is exactly the same. But I believe it's important for us to go through this again, because this is working on this stuff is one of the first steps for you to start manipulating a ton of symbols, okay, and feel comfortable about it, because if you just patiently have it go through each step, make everything make sense, and it all works out nicely. Okay, there's no need to be blown away by a boatload of symbols. It works the same way as numbers. There's no difference really, and so that's that. So with that, we have derived the formula for the hyperbola. Okay, which is now we know what is this. We're now we're still on page 821 right here, and so the standard form of the equation of the ellipse, okay, is this thing right here: x squared over a squared minus y squared over b squared equals to 1. So every time you see this equation that looks like that, then you know immediately that this thing is a hyperbola. And sometimes, however, the hyperbola, this is the one that runs horizontally, and it might flip over and become vertical. And if it does, then all that happens is the y and x change position. See, what used to be y is now x, and otherwise everything looks more or less the same. Now the ellipse, the hyperbola is is similar to the ellipse. It has various definitions, but there is one thing, however, the hyperbola has, is that it has that the ellipse doesn't, and that is they have asymptotes. Okay, and the asymptotes are called this thing right here. The asymptotes are given by y equals to plus or minus b over ax. And now why do they have asymptotes? It's because, let's look at the following page 822. Yeah, so I think I'll write that down here. Look at page 822, where we have some pictures of the ellipse. Hyperbola. I'm getting the things stuck in my head. So this is a standard form. Okay, this is that is a horizontal one. No, which one's horizontal? This one's horizontal. This one's vertical. Okay, if it opens left and right, that's the horizontal one, because then the a's are the determining factor. See, and when the a's are like top and bottom, that's the one that opens up. That's a vertical one. But they look, well, they look kind of the same. But in any case, you notice that there is these red lines, or orange, or whatever color these things are, that goes across. Those are the asymptotes of the hyperbola. That is, these graphs, as it goes to infinity, it will approach those lines. It won't touch it, I don't think, but it will get closer and closer to it, infinitely closer. So that those are like so those are the asymptotes, and the asymptotes are given, the formula are given directly here as this one is minus b over a, and the other one is a over b, or the minus one. Okay, the one leaning one way is the positive one, the leaning backwards is the negative one. So that is that's the only thing that the ellipse does not have, is because the ellipse doesn't go anywhere, it just stay put, so then it doesn't have any asymptotes. Whereas the hyperbola takes off, okay, in all four directions, so it will have asymptotes. Okay, so having said that, let's and the solution for C, the equation for C is similar to the ellipse, but there's a slight difference in that I guess we'll calculate C. I don't remember the ellipse. How did the ellipse go? I'll think about it later. And right now, let's just focus on the equation for this is right here, okay, the b equals to c squared minus a squared. That is for a regular ellipse, the one that opens left and right. The other one, the other one works the same way, because you just call a different thing. But we'll think about that later. Okay. Right now, let's. In other words, the the better way to remember it is perhaps c equals to a, for the hyperbola, is that c equals to square root of a squared plus b squared, because that's very similar to the Pythagoras theorem, so it makes it easier to remember. This is true for the hyperbola. Yeah, how did the ellipse go? We'll think about that later. Okay, right now let's focus on the hyperbola, one thing at a time. So let's look at example 1 at the bottom of the page. Let me erase the board first. So let's look at example 1 on page 822. We have y squared over 49 minus x squared over 32 equals to 1. And the thing is, this is the y is the positive one, is over the bigger number, which means this hyperbola is the vertical version. That is, it looks something like this. Okay, it goes up and down instead of left and right. But otherwise, it should run about the same way. What are we doing? We are identifying the vertices. Okay, so a squared equals to 49, and then b squared equals to 32. And so then a is equal to 7. Okay, a equals to 7. And then b is whatever square root of 32 is. And then c is a squared plus b squared, and then square root, which is this plus that, take the square root. So c equals to 49 plus 32, that's 81, the square root of 81, which is 9, I guess. So that is the hyperbola. Wow, they didn't even graph the thing. Seriously? I guess that's all they want is, so a, what do we have here? Well, anyway, so that's, yeah, the vertices are located, A is 7, so the vertex is equal to, being that it's a vertical one, then the main axis is vertical, okay? So this will be, x will be 0, okay? And then A is 7, that's the top point right here. And then the bottom point is x is 0, and then A is minus 7 on the y-axis. And then c equals to 9, and I guess that's all we have to do for example 1. Next, let's look at example 2 on page 823, where we have we need the equation of some hyperbola whose vertices are at plus or minus 6, 0. So the vertices are at minus 6 and 6, okay? Both has 0 on the y for y coordinates. So the hyperbola is going left and right. That is, it looks something like this. Okay, it goes this way, and that part of the hyperbola goes that way, something like that. That is quite ugly, but oh well. And then the focal point is, where's the focal point again? I think it's in here, right? And right, anyway, the focal point is some other measurement. Is 2 square root of 10, and then and the other side is negative 2 square root of 10. So what is the equation of this thing? All right, so that should give us enough information because we know this, okay? So we already know that A equals to 6, and the thing goes left and right. And then C equals to 2 square root of 10. So we just need to know B. So B, based on that formula, is, so B squared equals to C squared minus A squared, okay? So that equals to, that thing squared is 4 times 10, that's 40, minus 6, A squared is 36, so it equals to 4. And so B equals to 2. So the equation then would be x squared divided by over a squared, which is 36. Okay, being that this is a left and right hyperbola, x goes in front with over the bigger number, which is the 36, 6 times 6, minus, okay, remember the minus. We're not doing ellipses anymore, and hyperbolas have to do a minus. And y minus y squared over b equals to 2, so b squared is 4, and that equals to 1. And that is our equation, because our hyperbola is centered at the origin, so we don't have to think about anything else. And that's example 2. Yeah. And that is what we have. See? Yeah. There is a graph on the following page that looks similar to what I have over there. So that's example 2. I will finish this section in the next video.